So award is there for UG as well as for PG. So this session will be chaired by Professor K.J. Vinay, Professor in Indian Institute of Science, Bangalore, and co-chair for this session will be Professor Amlindu Patnaik, Associate Professor in IIT Roorkee. So now I hand over session to session chairs, please.
Good afternoon. Welcome to all of you for this session 2. As you have been told, it is partly UG and PG students. And my understanding is that all the speakers will get about 5 minutes for presenting their work and maybe 1 or 2 minutes for interaction with the audience. And since this is for an award, I request the members of the audience to not to interrupt the speaker during the 5 minutes that they have and ask the questions afterwards. And we may try to cut it off if it goes beyond, let's say, 2-3 minutes. The interaction session goes beyond 2 or 3 minutes. So we will get started. I suppose all the presenters are here. All the papers have been loaded. The first paper in this list is on a compact low-pass filter with a wide stop band based on defected ground structure. The paper is going to be presented by Ms. Manisha Arora.
सर ये वो बार-बार लगाना पड़ेगा। हाँ ये यस वो बार-बार लगाना पड़ेगा।
Good evening, everyone. I'm Manisha from University Institute of Engineering and Technology, Kurukshetra University. And on the behalf of my team, I'm going to present a compact low-pass filter having the wide stop band using defected ground structure technique. The basic objectives of a low-pass filters are less complexity and the compactness in size, wider stop band, less passband ripples, and the less insertion losses. So, fulfilling the objectives, I have used the defected ground structure technique. This is the design and the design parameters. I have used the low-pass filter as the step impedance Chebyshev low-pass filter. As the microstrip line is not uniform and it is varying in width, the lower width is having the higher impedance and the higher width is having the lower impedance. So this is the low-pass filter, and enhancing its properties, I have used 3 DGS units. One is the paired U-shaped structure, which is connected by a rectangular slot, and in middle of these two symmetrical paired U structure, a double arrow-headed structure is used. And these are the design parameters for the DGS units and the microstrip low-pass filter. So analytical results, what the DGS units are doing is, if we want to have the desired cutoff, the length of the U-shaped defect is kept maximum. What it does, it increases the inductance value of the microstrip line. And for increasing the sharpness from pass band to stop band, I have kept the width of the rectangular slot that is connecting the U-shaped defect. It is kept minimum, which again increases the inductance value, keeping the resonance frequency value constant. And to have the wider stop band, the width of the slot connecting the two triangles of the arrow-headed slotted structure is kept maximum. That will also increase the inductance value, but it decreases the capacitance value. So these are the simulation results showing the cutoff value and the stop band, wider stop band, and having the sharpness from the pass band to the stop band. The cutoff is shown at the minus 3 dB and stop band is from minus 10 dB value of frequency. So what is the novelty in design? Basically, when we are using a higher number of DGS units, the pass band ripple increases. We are, of course, decreasing the size of the any device using the defected ground structure. But when we are increasing the number of DGS units, then the pass band ripple increases. So remove the pass band ripples. We have to improve the structure by cascading low pass filters. But it will increase the size. It will increase the device size. So these structures are used. Parametrics are done on these 3 DGS units, and the results are got with the required cutoff value, the wider stop band, and the sharpness from the pass band value from the pass band to the stop band. These are the experimental results. I have used the VNA to check the experimental results for S11 and the S21. And this is the comparison for in the simulation and the VNA results for S21 and S11 again. So I have got the cutoff frequency of 2.4 gigahertz, a sharp cutoff, and a stop band from 2.83 gigahertz to 11.46 gigahertz. Insertion losses are less than 0.6 dB from 0 gigahertz to 2 gigahertz, and this compact size of the filter is 30 mm to 30 mm by 20 mm. So the future scope of the low-pass filter using the defective ground structure is, low-pass filter is basically the base of any type of filter. So splittering resonators, which are used for the metamaterial synthesis, is having the same configuration as the open-loop dumbbell shaped bandpass filter. And if we are using a patterned ground structure, then there will be the less signal losses, which are due to the dielectric losses in RFIC. So this is the future scope for the low-pass filter using DGS, and these are the references I have used for the low-pass DGS filter. That's it. Any queries?
Questions, please.
If you use 50 ohm line instead of low impedance line, what happens?
If you are using the 50 ohm DGS line, then we have to increase the inductance value by using another DGS.
You just use 50 ohm line in that
Yes, sir.
in signal instead of you are taking low impedance
Then we
line.
will be getting a better one-pole response. Other than this,
Not like this. I think the insertion loss will increase. I will check it with you. Normally we use 50 ohm
I
line.
have not
first,
used
use
DGS
that
line
with
with this 50 ohm line. I have used it for a stepped impedance line. But
without step impedance line, low impedance line.
yes, sir.
If you just put 50 ohm line only, the risk part is there. Just is the same as that. Then what
Maybe,
happens?
but parameters of DGS units have to be
I
changed.
just request you to study these things. It may give you insertion loss in the range of 2 dB or something like that.
It is being recorded.
Any other question?
Is a point.
0.6 dB. 0.6 dB.
Any other question?
With your filter, it is very much.
What were the specifications of the filter with which you started?
Sorry, sir.
specifications of the filter with which you started.
Chebyshev low pass
You
filter.
have given the end results. What were the specifications?
Specific results were we have started with stepped impedance low pass filter, sir. Then I have then parametrics from DGS units.
Filter specifications.
So you mean L and C values? Cutoff frequencies. I have shown it as 2.4 gigahertz in final values.
You have shown what you have obtained.
Yes, sir.
What is the value with which you started with?
I have
What was your
started
aim? What was your aim?
I was getting a cutoff frequencies more than 2.5 gigahertz, approximately 3 gigahertz I have obtained without using the DGS units. No, filters, in filters return loss is not important, insertion loss is very important. Insertion losses are important. Insertion losses are more important, sir, in case of filters.
Everything important. One thing, suppose someone given some data for designing something, then how you can reach there? So someone giving, suppose cutoff is 3 gigahertz, then how you get the dimension out of it?
Okay, I have started, first of all, I have started with parametrics on DGS. You have starting the question, if you are using the 50 ohm line. I have done the parametrics for the 50 ohm line. Okay. Yes, sir. Yes, sir.
How you are going to determine the dimension of the filter? What is the dimension of the
Slots and other things.
and what is the dimension of the
So I have calculated it by the equations of L and C.
How do you do it?
I think we'll close this paper. We'll move on to the next one. The second paper is design of a new low-cost metamaterial structure, dual band, E-shape, suppose antenna. The word is missing here. It is by Ripu Daman Singh and Vipul Sharma. I request the presenting author to come on. Ripu Daman Singh. Hello.
Good evening, professor, researchers. First of all, I like to introduce myself. My name is Ripu Daman. I am a BTech student at Faculty of Engineering Technology, Gurukul Kangli, Hyderabad. My subject of my work is design of a new low-cost metamaterial structure. Here we all are familiar with the unusual properties of metamaterials. But the problem with metamaterials are that in our colleges where the labs are not sufficient, it is not possible to design like SSR in microwave and micrometers. So for that we have designed, we propose a structure that in millimeters, and also the fabrication cost and the material costs that are going to be used is very low. So our objective is to design a low cost and easily fabricated structure for a metamaterial. Before I go to next slide, I like to tell that I have done only the simulations on HFSS. I have till now we don't have any experimental or analytical result or any numerical approach to explain what is going behind this structure. We just use HFSS and the results are I'm going to show you. Here, there is a as your structure in which we use two plates, substrate plates of bakelite, and in which steel spheres are imposed. Here a unit cell of dimension 2 mm into 2 mm, and the thickness of the substrate is 2.22 mm. Has some parameters and the dimensions of the cell. For analysis purpose, we use 9 unit cells to analyze the structure. The novelty in our design is first thing is easy design procedure. For designing this substrate, what we are going to do, we take two PCB plates first of all, and then remove the metallic sheets from PCB plate by itching, and then we are going to create half sphere on both of the plates, and then going to join them. So there are two plates, each having dimension thickness of 1.11 mm, and then there are spheres of steel that we obtained from the nip of the pen, and the dimension of the sphere 0.5 mm. The specification when we buy a pen, then on its box there specifies the specification of the nib. It is either 0.5 or 0.6 or 0.7. So our motive is to design the metamaterial or design the structure from things that are easily available in the market and can be easily fabricated in our lab, because PCB plates, which is bakelite, easily available in our lab. And second thing, to drill to this half sphere, we only need a PCB drill machine that's easily available in any college. So we create this half sphere, and then join these two plates to create a sphere in which we place a steel ball. This is an analysis setup. We place the structure in waveguide and then find the S parameters. From this S parameters, using IAW technique, we find permittivity and permeability, from which we find then refractive index. Here we have the analysis results. The metamaterial tune at 4.2, 6.5, 8.7, 10.8, and this. After the simulation using NIW technique, we find the permittivity and permeability. Here are some sample values. We take different values at different frequencies and form a table in which both the permittivity and permeability both are negative respectively. Using permittivity and permeability, we find refractive index, and we obtain that the refractive index is negative in this region, and here I show the range in which the refractive index is negative, and the maximum refractive index in this region, and the frequency at which the maximum refractive index is obtained. So here we prove that the structure that proposed is showing the negative refractive index, and due to this negative refractive index, this structure can be used to improve the performance of the microwave antennas or any other devices. That the feature scope is just using this antenna, using this substrate substrate for a patch. The bandwidth of the antenna is increased from zero point 0.3 to 0.7, and then this type of substrate and antenna can use for improvement in microstrip antenna for its directivity, and also for, it works as a convex lens. Thank you.
Questions, please. Sorry, you will ask only one question.
I have a suggestion that let me contact, discuss with others instead of asking, giving the chance to discuss with others. But
The unit cell.
discuss with other people instead of putting him through the rigors of question answer.
Answer should be given by us.
No.
Not us.
What? This is our setting. They should be asked questions. Okay. We can give them 2 minutes to 3 minutes, but one question at a time.
Well, you choose a number of unit cell. That cell is you are talking about. You have to do certain drill on your PCB. That whole, how you choose that whole dimension. How you choose, because there are perhaps 9 unit cell you have used.
Yes, sir.
Yes, 9 unit cell you have used. How you choose the dimension of that unit cell, and how you think to fix on your PCB that ball.
Sir, actually for a metamaterial, unit dimension must be chosen so that the the range in which we are going to work should the dimension and the ratio of the wavelength and the dimension should be around 20 times or 10 times, so that the other phenomena like scattering or reflection not, because if reflection or if scattering is done, then the result is not.
No, no, my question is how you choose that unit ball. How you choose? What is your procedures? Suppose somebody would like to design this type of antenna in certain terahertz range, then how he should go for to design this type of antenna?
Actually, all these
What are the procedures?
the dimensions and all these. Suppose if I give an example, I have chosen 1.11 mm. The thickness of the substrate is the thickness of the substrate when we remove the metallic plate from the PCB. So we just use all these things that are available. That's why I'm in the starting I tell you that we don't have any numerical or any experimental result on this. We are going to do that experiments and in future.
Okay. But we will move on to the next paper.
Thank you.
The next paper is interaction of RF from mobile antenna with brain waves. This is going to be presented by Jagpreet Kaur.
Good evening, everyone. The topic for my presentation is Interaction of RF from Mobile Antenna with Brainwaves. My name is Jagpreet, and I'm doing this project under the supervision of Professor Patnaik. Starting with an objective, the experimental study of RF exposure from mobile antenna on EEG signals is done, and the second is to compare the effect of 2G and 3G mobile radiation effect on the EEG signals. As we know, there are a number of multiple exposure effects observed on the human brain, but the mobile is used in very close to our head, so we are concentrating our study on the human brain. Also, it was observed by one of the experts, Winberg, who said that our brain acts as an antenna. So, the main objective here is to study the effect of RF on the brain. This is a design methodology where first picture shows data acquisition system. Here the wires are shown, the electrode wires, which are connected to the scalp as per this 1020 system. Now FC, SEZ, PZ, this middle line shows the electrodes placed on the middle of the hemisphere, dividing the left and the right hemisphere. Similarly, other electrodes are placed according to the same template shown. And this is the recording going on where the person is holding a mobile in the right hand and the exposure phase is being recorded. At the back side, the lines which are shown horizontally shows the EEG recording. And the novelty design here is we are studying the effect of 3G, which is not studied until, or the very less study is done on 3G. Also, we are comparing the effect of 2G and 3G simultaneously. And the table shows here is we are recording the EEG in sham 2G transmitting, 2G receiving. We are transmitting is when we are making a call, and 2G receiving is when we are receiving a call. Similarly, is for the 3G mode. So 2 minutes recording for all the 5 different types of exposures is done. This is experimental analysis where data analysis is done in 3 different steps, starting with the pre-processing, where the raw EEG is filtered and then the FFT is taken. This is a raw EEG where we can see there is noise, artifacts, and we filter out these artifacts to get the clean EEG. Then we convert it into frequency domain to get the power in different psychological bands. And this is the FFT analysis where we can see the first column shows C3 during the baseline. That means the power, alpha power at the C3 node is 16 on an average, 16.802. That is bolded. And then the third column shows C3 2G. That means the C3 alpha power at C3 during 2G mode. So that is increased from 16 to 24, which is a significant increase. Whereas the second last column, C3 3G, shows there is increase that is only 17.37. So the drastic change is observed during the 2G exposure, but 3G shows a very small increase. Similarly for the other electrode points. Here graphically representation where blue line shows the baseline when there is no exposure and red line shows the 2G mode when the alpha power is increased drastically, whereas green line shows 3G exposure. So the exposure is affecting in 3G mode also, but the effect is almost half, you can see here. Also I've done statistical analysis using SPSS where the red arrow is shown, it is minus 0.49. That is the correlation between the left and the right hemisphere in the temporal lobe. As you know, the brain is divided into different lobes. So I'm specifically telling about your temporal lobe because the major effect is observed there. As you can see, minus 0.049, and during 2G it is changed to 0.495. That means polarity reversal is seen here. So that means when we are, mostly when the people we ask, they are right-handed. That means their brain is left dominant. So here firstly you can see the dominance is changed. From left dominant, the person is changing to right dominant in 3G. Also the effect is seen, but the change is very small. So analytically, results include that the alpha increase is observed when the event is evoked. But here when we are giving an RF exposure, also an alpha increase is observed. That means there is a cognitive decline during the RF exposure. Also the second point here is there is IQ decrease when an alpha increases. That means they are inversely correlated. So it is affecting your learning, memory, cognitive decline is there, problem solving. So the person's memory is affecting in this case. Here I have compared my results with the other previous researchers where the same trend is observed. Firstly, there is an alpha increase. Also, the conclusion in my study is also there that 2G is affecting more than the 3G. Also, correlation is more affected in 2G than the 3G. So, from conclusion, here we draw is the 2G keeps your brain much more balanced as compared to 3G keeps your brain much more balanced as compared to 2G. The future scopes is there. We can do a double-blind study where a single-blind study was done. There are very few studies on 3G done till yet. Also, there we can use RF exposure for even treatment of diseases like Alzheimer's. So these can be further done. Thank you. Any questions, please?
I have a question. Sir, please one. I have a question.
Excuse me. You showed some comparison with the existing literature results.
Yes, sir.
Are those comparisons
satisfactory enough to validate or justify your results?
So yes, as we can see, from 2002,
Because
it
there are too
was
many, we cannot justify right now. You justify.
yes, sir. Firstly, there is an increase in alpha, which is seen in almost all. Only there is a second row which shows a little different effect, but the protocol they were using was not proper. So, leaving the second column, you can see everywhere there is an increase in alpha. So from there you can see the same trend is followed everywhere. But additionally what I have done is, you can see the correlation is more affecting in 2G than in 3G, and also the power, alpha power was more affected in 2G than in 3G. That are the additional what I have concluded in this. Also, there was analytical results where I have concluded that it is affecting our memory. So there is a cognitive decline, which I have studied from some psychological papers. The people in psychology, they are working on the alpha band. They are finding out what the alpha band designate for, why do alpha band be studied for. As alpha band is much more related to your memory. So it is related to IQ, and IQ and alpha band are inversely proportional. So that means when we are increasing the alpha, IQ is decreasing. And IQ is directly proportional to learning, memory and problem solving. So from here we can conclude increase in alpha is affecting our memory.
Okay, I think we'll move on to the next one.
Sir, I have a question.
You can ask them after the. It was the time limits, that is why I'm proceeding to the next one. So, the next paper is Krishna Ratha, Umesh Soni, and the title is a novel moderate size UW. Oh, sorry, the next paper is S. Manoj, ultra wideband spectrum monitoring using spanner shaped UWB patch antenna and energy detection algorithm. The paper is by S. Manoj.
Good evening, all. My name is S. Manoj, and I'm a tip student of VN8. My topic is ultra wideband spectrum monitoring using spanner shaped UWD patch antenna and energy detection algorithm. So, UWD communication has emerged as a very potential candidate for quality ready technology recently. So, my first part is with the design of ultra wideband antenna for 2.232 to 11.43 GHz. I'll also discuss the return loss radiation pattern and gain results. Second part is with the implementation of energy detection algorithm in LabVIEW. The third part is with combination of the algorithm and the antenna and the complete hardware set. This is my antenna. I've also fabricated the antenna. So from different papers, I've concluded that elliptical shape will give much more bandwidth results than rectangular patch antennas. That's why I started with elliptical patch antenna. Also, I've kept the ground plane finite to increase the bandwidth. There is a small gap between the ground plane as well as the top patch. This gap is accumulated to reduce the coupling between the ground plane and the top patch. I've also cut two slots in ground plane as well as the top patch. These are for also increasing the bandwidth. Since I received two bands where the return loss was less than -10 dB. So from a paper I concluded that using specific slots we can achieve band stop characteristics. So with the help of those papers I've added these two slots, and then using parametric analysis in HFS software I've exactly modeled to receive a wideband characteristics. These are the simulated results. These are the measured results. As you can see, there is a slight variation in the measured results. I think this is due to the improper soldering of the connector. I think a proper temperature controlled soldering would ensure me a better results. I'm receiving minus 10 dB response till 9.7 gigahertz, but in between from 8 to 9 gigahertz, I'm slightly having slightly greater than minus 10 dB responses. This is my radiation pattern, which was omnidirectional pattern, and my gain is about 3.3 dB. This is the algorithm part. So this is the energy detection. I've implemented energy detection sensing in IAW software. This is the algorithm. This is the entire setup actually. So this what you see is NI PXI chassis along with NI VSG module. So what it does, it has a VSA and VSG built inside this module. So first I will generate a QAM signal of particular carrier frequency. Then it will be received using the ultra wideband antenna which I fabricated, and then it will be checked whether the carrier frequency is properly sensed or not. So I've implemented the algorithm in LabVIEW, and both are interconnected. PXI chassis and LabVIEW are interconnected through host communication. So this is the QAM generation front panel in LabVIEW. This is the corresponding block diagram implemented in LabVIEW. This is the spectrum sensing front panel which is implemented in LabVIEW. As you can see, it shows the star spectrum density with the peaks. The peaks is actually the carrier frequency signal. Simulated this from the module. RF module actually supports from 400 megahertz to 6 gigahertz only. So prepare the code as per the basis. So I've tested different frequencies from 500 megahertz to 6 gigahertz, all QM waveform signals, and I've properly sensed all those things, and it satisfies. This is the corresponding block diagram of the sensing algorithm in lab. This is an OT. I've implemented a complete setup for ultra wideband spectrum monitoring from antenna level to the algorithm level with the help of NI-VST module. Proper function of antenna is established using suitable application. This complete setup can be used as a part of cognitive radio application. Future scope: the proposed antenna design can be further improved by careful temperature control soldering of SMA controller. Also, filter with band stop characteristics can be added to avoid interference from the unlicensed bands like 5.152 to 5.825, those gigahertz range. The entire setup can also be enclosed in a smaller customized RF front end, like similar to SDR platform. This also can be performed. These are my fronts.
How did you verify your design about the power you're transmitting and the energy received over here? Did you confirm their results?
Yes, sir. So in this, I can set my power reference level. So an actual signal is actually generated by this module. This is the entire setup. So I'm transmitting the signal using that antenna. That's also a wideband antenna supporting from 400 megahertz to 6 gigahertz. So I can do the experimental setup actually for this band only. So an actual QM signal is transmitted by that antenna. It's received by my UWB antenna, and it will be processed using LabVIEW. So I can set my reference level, power level in here as per the code, which will be directly reflected in the hardware part. Then I can set my start frequency, stop frequency. I can set my carrier frequency of the signal.
No, what I'm asking is, did you use Fritz's equation to find out that this should be the signal level received?
Yeah, I've changed carrier frequency from, like, I've swept the carrier frequency from 400 megahertz to 6 gigahertz, and I've received that the LED indication that you can see is properly indicated. It means indicating the signal correctly.
Your simulations are from 3 to 10. But the experimental result is limited up to 6 gigahertz only.
Yes.
So you do not have any comparison between 6 to 10.6.
Yes. Apart from the S parameters, no, because that hardware supports only up to 6 gigahertz.
If anybody has, we can have probably one question. All right. All right. We'll move on to the next paper. This is a novel moderate size UWB antenna for radar applications. It's by Krishna Rathore and Umesh Soni.
A very warm good evening to one and all. Myself Krishna Rathore from Government Engineering College, Ajmer. The title of my paper is A Novel Moderate Size UWB Antenna for Radar Applications. My main motive was to design an antenna which could be used for the frequency band of UWB as well as for X band. The range of UWB band is from 3.1 to 10.6 gigahertz and X band from 8 to 12 gigahertz. Now, the main motive was that so that the antenna could be used for various wireless applications in UWB range as well as for specifically for radar applications in X band. Now moving on to the design and design parameters. Basically the design was a transition from a narrowband microstrip antenna to an ultra-wideband antenna covering the range from 3 to 12 gigahertz. In the design, there is a patch which is of moderate size and the main resonating frequency was 9 gigahertz. A narrowband resonating frequency initially was 9 gigahertz and according to that, the dimensions of the patch appear to be a square 40 cross 40 millimeter. Now, since it was a transition from a microstrip antenna to ultra wideband, the ground was partially cutted and there is a notch in the center and some stairs at both the sides. Now, since it was a moderate size antenna, not very cost effective, to make it cost effective, I just tried to cut slots in the patch in order so that the material used, it decreases. So after that, a parametric analysis was done. Almost all the width and length of the slots were varied. The substrate used was Rogers 4003, having dielectric constant 3.55. The substrate thickness used was 0.812 millimeter. These are the parameters of the design. Now, novelty in design. Although such type of antenna, you can say that there are many such types of antenna which covers this range, right? But this antenna, first of all, the size is moderate and also a very good impedance matching is obtained. As we will see in next slides, you can see the parameters. W1 is the width of the slot in the patch, the eye slots, and W2 is the width of the center notch in the ground plane. Both these parameters are varied, and we can see that when W1 and W2 varies, the higher frequency, it decreases in both the cases. Next, L2 is the length of the central notch in the ground plane. As L2 increases from 1 to 4, the higher frequency, it increases. Also, the gap between the patch and the ground plane was also varied because it is a very important parameter. As we can see in the result, the value of G is varied from 0.7 to 1, but the most optimized value obtained was at point A. The impedance matching was minus 52 dB in this case. So I have chosen the value of the gap between the patch and the ground plane, 0.8 millimeters. This is the optimized return loss curve. As we can see, the range which this antenna is covering is from 2.7 gigahertz to 12.5 gigahertz. The VSWR results show that for this entire range, the value is well below 2. These are the radiation pattern results. We can see that the antenna is giving nearly omnidirectional radiation pattern in both the planes when phi is 0 and when theta is 0. In analytical results, the antenna is covering the expected frequency range from 3 to 12 gigahertz. The results are very optimum, and the VSWR results are also expected. Conclusions and highlight: since we have used moderate size and we know that bandwidth and size is inversely proportional. Size is more, the bandwidth should be less, but we are getting the expected bandwidth and all with a very good impedance matching factor. So this is most important, and also the cost effectiveness has been taken care by removing the unwanted slot from the patch where the surface current density was not very much. These are the top references. Thank you so much.
What software you have? What software you have used?
Sir, CST.
No, this you are saying that size and some bandwidth size increases, bandwidth decreases, like that. You were saying something.
Yes, sir.
I could not follow.
So there's an inverse relation between size and bandwidth. As the size of the antenna increases, the bandwidth decreases. That is why we had transition from microstrip narrowband antenna to ultra wideband antennas. Basically, the ultra wideband antennas, they are compact in size, right?
If you take, see, I'm considering a simple antenna, not this structure. Say you have a horn. If you reduce horn antenna, very simple antenna. If you reduce the aperture size, you mean its bandwidth will increase?
So I'm talking about patch antennas.
Whatever antenna you are using, bandwidth is related to Q factor.
Yes, sir.
Q increases, bandwidth decreases or increases?
So they are inverse in relation.
They are inverse related.
Yes, sir.
Now Q, if you know the Q's limit, Q's formula, Q and size, are they related? They are directly proportional or inversely proportional?
So they are directly proportional. So they are inversely proportional.
Combination of patch and slotted patch. I don't understand. It is, I think it is a flat monopole, right?
Yes, sir.
Then why do you call it a patch?
So it was, sir, it is a square monopole patch antenna in which I have cutted slots. And
Could
slots.
Could you please show me the ground plane?
Yes.
It is the actual printed monopole. You should not call it microstrip patch.
Yes. So slots are basically cut because and the surface current.
It is printed monopole. If you call it a patch, microstrip patch, that it means different configuration.
All right.
Okay. What about the gain of this antenna?
So I haven't included the gain result.
You are no. I'm telling you, you are working over such a wide bandwidth. and you have shown only one radiation pattern. That is not sufficient. You want to see at least in regular interval what type of change in radiation pattern. That's very important.
So I've included the radiation pattern at the resonating frequency, that is 9.6 gigahertz.
It is ultra. It is a wideband antenna. So why do you consider it as a resonant frequency?
So from where I started.
Anyway, you'll have to learn all this thing. Okay, thank you.
All right, so we will move over to the next paper. This is on a new reconfigurable 8-armed star patch antenna by Monica Arora.
A very good evening to all and everyone present here. I am Monica Arora, pursuing MTech dissertation under the guidance of Professor S.S. Today I am here to present my paper on new reconfigurable 8-armed star patch antenna. The objective of the designed antenna is to design a reconfigurable microstrip patch antenna that exhibit frequency tuning and radiation pattern alteration. Reconfigurable antennas are required in those applications which require switching from one application to another. It is designed to operate in X-band application. This is the structure of antenna. It has an octagon-shaped patch. It has an octagon-shaped patch of each side 1.82 centimeter. 8 triangular slots of dimension 1.05 centimeter and 0.95 centimeter with a base of 0.4 centimeter are cut out of the patch. Then to incorporate switches, we cut out 8 rectangular slots of dimension 0.8 and 0.2 centimeter. The substrate used is Roser's artiduroid of thickness 0.078 centimeter with a relative permittivity of 2.2 and the dimension of 4.7 into 4.7 centimeter. This is the design of antenna using switches. Here in this, a metal strip is used in place of switch. The presence of strip indicates that switch is on, and the absence of switch indicates that switch is in off state. Novelty in design. It is a new 8-armed star structure. A wide band of 6.4467 GHz is obtained. It is having a reduced size and moderate gain without reconfiguration. Metal strip is used to reconfigure the antenna. A multi-band of 4.0118 GHz, 902 MHz and 1.593 GHz is obtained after reconfiguration. This is the simulated return loss characteristics of antenna without having switches. A wide band of 6.4467 GHz is obtained in the range of 8.1093 GHz to the 14.5560 GHz. This is the simulated return loss characteristics of the antenna having switches. After reconfiguration, 3 bands are obtained. First is of 4.0118 GHz, second is 902 MHz. This is first band from this to this, and second band 902 MHz, and third band is of 1.5938 GHz. This is the simulated elevation gain pattern of the antenna. The first one is for the antenna without having switches, and the second is for antenna having switches. The first pattern I had shown. I place the marker on each and every frequency, and the gain is positive in all those frequencies. A maximum gain of 8.4323 dBi is obtained at resonate frequency 8.95 gigahertz. And after reconfiguration, the gain is 7.2524 at 9.2 gigahertz, 5.3123 dBi at 12.95 gigahertz, and 4.2819 dBi at 14.8 gigahertz. And this is the azimuth pattern of the antenna having switches or without having switches. The gain is again positive in above stated resonating frequencies. The conclusion, use of switches alter the result to a great extent. After reconfiguration, multi-bands are obtained, and the antenna can be used in X-band applications. Future scope, we can change the state of switch, like we can use 2 or 3 switch instead of 8 switches without affecting the radiation pattern. So for this we can use the graph theory to reduce the redundancy in the structure without affecting the result. Thank you.
Question?
Excuse me. Excuse me. Excuse me. Hello. The question first will come from this paper. After that, others can ask the questions.
Okay. So it looks like that you are trying to study that if you have a particular antenna and you are introducing switches in that,
yes,
how the resonant frequencies are changing and how the radiation patterns are changing. Are you able to design it for a particular, let's say, frequencies you want to achieve, reconfigure it for particular frequencies or particular type of radiation pattern, or just like you want to study something? Can you explain that one?
So we can use graph theory to change the state of. We can activate 2 or 3 switches at a time instead of all these switches.
Do you have any design in mind, some specifications?
Sir,
another
design?
Did you have any specifications to start with, or just you are studying some phenomena?
No, sir, I read the papers related to this.
How did you determine the shape first? Was it provided in the literature, or you have arbitrarily taken some shape?
Sir, I take the help from these references.
Which parameter is reconfigurable in this?
The frequency shifting and radiation pattern alteration things.
Any other questions?
Yeah, you mentioned about the expand applications. That's Professor Ramesh Garg has been mentioning that. Did you have anything clear in your mind that what application you have been focusing? Then only the specification comes out of it, right?
Sir, I have designed this antenna for expand applications.
Yeah, but expand application means anything in mind?
For satellite applications.
Satellite, you need to have a reconfigurable. Means what are the specifications you need for? What kind of reconfigurability parameters you are looking for?
Frequency shifting. I just want to shift the frequency.
Just one comment for you. Actually, you are the beginner, so you'll have to learn many things.
Yes.
First one is the resonant mode. Second one is polarization. Two major issues are missing in this antenna. You have to first understand these two parts. Okay.
So yes, 3.
Those two are absolutely missing. Moreover, actually, I was apprehending about the cross pole. Anyway, the main radiating modes are not very clear. Actually, there are multi-mode operations are going on. Moreover, the polarization, that is the major issue. Okay.
Yes,
Okay, thank you.
The next paper is dual band E-set microstrip patch antenna for WiMAX and WLAN applications. The presenter is K.N. Jyoti.
Good evening to all of you. My name is Jyoti. I came from Graphikira University, Dehradun. Currently, I am pursuing my MTech thesis work. The title of my paper is Dual Band E-shaped Patch Antenna for WiMAX and Wireless LAN applications. The objective of the paper is to design a dual band patch antenna which is suitable for simultaneous using both WiMAX and Wireless LAN applications. As the topological shape of the antenna takes the letter E, the name E-shaped patch antenna. Here to start with, initially a simple rectangular patch antenna which is useful for using 5.5 GHz wireless LAN applications is designed. The initial dimensions of the patch are obtained using classical design equations of transmission line model. And the design antenna is fed using coaxial feed, coaxial cable feed, due to its advantages such as it's easy to fabricate and easier to match with input impedance. Here, in order to obtain the additional resonance at 3.47 GHz, two rectangular slots have been inserted in the patch at the radiating edges. That gives a dual band operation. In here, the antenna is designed on a FR4 substrate having dielectric constant 4.4 with a substrate height 1.524 millimeters. And here this figure shows basically the dual band operation of an E-shaped patch antenna. Ordinary patch antenna, it can be modeled as a simple LC resonance circuit. Due to slot cutting, there is change in the surface current distribution, and the equivalent circuit of this patch changes from single LC resonance circuit to dual resonance circuit. If the resonances of these two LC circuits are coupled with each other, it forms wide band. If the resonances are apart, then it forms dual band operation. Basically, slot antenna performance mainly depends on the slot dimensions, that are slot length, width, and position of the slot. After careful parametric study of all these dimensions and also the feed locations, I optimize the dimensions for the performance, for the objective performance. And these are the total dimensions of the antenna, and all the dimensions are mentioned in millimeters. Novelty in this design is that, unlike ordinary patch antenna, which resonates at single band of frequencies, the proposed antenna resonates at two different frequencies, and these two frequencies are suitable to cover two different wireless standards, and these standards are WiMAX and wireless LANs, which have been widely used as viable, cost-effective, and high-speed data transfer solutions in mobile phones such as smartphones. And compared to other methods of getting dual band operations such as stacked patches and patches with more than one radiating element, the slot antenna is easier to construct. And the design antenna is simulated using CST software for the important antenna parameters such as return loss, VSW, surface current distribution, radiation pattern, and gain. The first figure shows the return loss plot, return loss versus frequency plot. From this plot, we can clearly see two resonances are occurring. One is at 3.47, which is close to 3.5 GHz, and other is at 5.5 GHz, with an appreciable amount of return loss of minus 27 dB and minus 25 dB. And the next plot shows this VSWR plot. For good antenna performance, any VSWR value less than 2 is considered as good antenna performance. Here, for this proposed antenna, at both the resonant frequencies, the VSWR is obtained close to 1. And the next figure shows the surface current distribution. Here at lower resonant frequencies, that is at 3.47 GHz, the current is taking longer path due to the slot cutting. Longer the surface current path, lower the resonant frequency. Whereas in case of 5.52 GHz, the current is mainly confined to the middle part of the E patch. And these are the simulated 3D radiation pattern, and this is the gain versus frequency plot. And gain obtained at 3.47 is 6.17 dBi, whereas at 5.5 it is 5.12 dBi. And these analytical results, due to slot cutting, the surface current is forced to take on longer path, and this results in the lower resonant frequencies. And these simulated VSWR values are showing good impedance matching between the antenna and the coaxial cable. And the conclusion of the study is, in this paper, a simple probe-fed E-shaped patch antenna is designed to suitable for WiMAX and wireless LAN applications. The impedance bandwidth is 2.3 and 2.2% at the corresponding resonant frequency. The future work is that as the antenna is showing narrowband characteristics, it can be further modified to use as a wideband antenna by inserting further slots in the patch or in the ground plane, and also the design antenna can be further extended to use in array configurations for use in MIMO applications. These are the references that I used. Thank you.
Open for questions.
That the lower resonant frequency is because of the slots and the current takes a longer path. Alternately, if we think that one of the resonances is due to the central portion, and other resonance could be the whole of it, forgetting about the slots, will that be okay?
No, it's mainly because of the current has to travel from feed point to the top and bottom edges around the slots. As the current is taking longer path, it is responsible for the lower resonance.
Could you match the longer path length with the resonant frequency with the lower resonant frequency, or
No.
it is just a qualitative explanation?
No, sir. Actually, because of this slot cutting, because of increasing the length of the slots, length of the current path, additional inductance is added in series with the resonance. I mean, additional resonance will be added with additional inductance will be added
basically bicon, half of the bicon antenna. As long as you carry the angle between these two, it is, I believe it is isolated and the angle is almost around 60 degree. It should give, if you can identify the feed location, it should give a broad bandwidth, because it is basically a half of bicon or discon. Since it's a planar version, you can say it's a bicon. It usually gives a wide bandwidth, but you are getting only two discrete peak. That is, for my suggestion, you can carry out the future study. It's not something what you have got. It does not correlate to the existing thing, as far as my knowledge goes.
Okay, sir, I will study on this.
Okay, thank you.
Thank you, sir.
Next paper is Miley set microstrip update antenna for multiband application. Oh, sorry. The metafractal based log periodic set antenna, and the author is Salim.
Very good evening to one and all present here. Today I, Shalini Pitta, student of MTech, is here to give my presentation on my thesis work, that is metafractal based log periodic shaped antenna. Well, beginning with the objectives, I need to design a metafractal multiband microstrip patch antenna and to show the same fractal geometry has a metamaterial behavior, and then simulate and fabricate the proposed antenna. In the next slide, I am giving the design and the design parameters. The upper figure shows the proposed metafractal antenna, and the proposed antenna is a new multiband antenna based on the square ring fractal antenna of 2.56 by 2.56 centimeter patch size, and the substrate uses artilleroid with the dimension of 4 by 4 centimeter, and the thickness is 0.0787 centimeter with relative permittivity of 2.2 and loss tangent 0.0009. Well, the novelty in the design is that it is a reduced size and multiband antenna, log periodic shape. Metafractal antenna, which I have designed, is a hybrid of metamaterial and fractal antenna. The fractal antenna will show the metamaterial behavior using a phase reversal graph. These are the simulated S11 parameters. As I told, it's the fractal geometry. These are having the multibands starting from 3.43, then 4.78, 6.3, 9.86, 11.04, 12.23, 13.41, and 14.6 gigahertz. These are the elevation pattern and the azimuth pattern defined for the resonant frequency in the previous slide. Then again, I have shown the gain versus resonant frequency plot, and the gain is considerably increasing, considerable for all the resonant frequencies. This is the 3D radiation pattern. The 3D radiation pattern is also shown for the proposed antenna at different resonant frequencies. As I have already told, it is a metafractal based antenna. It is a new concept where we are adding the advantages of metamaterial and fractal geometry. The metamaterial phase reversal property is shown over here, where this figure shows the reflection coefficient S11 and the phase reversal S12 characteristics of the metafractal log periodic shaped antenna. The designed antenna has phase reversal from plus 180 to 180 degrees, negative 180 degrees in the resonant frequency band, that is 4.7874 GHz and 13.4162 GHz, thus justifying the metamaterial behavior of the antenna in the same design. Well, concluding and the highlights of the achievements, this is a new metafractal log periodic shaped antenna which is designed and fabricated in this my thesis work, and the azimuth and the elevation radiation pattern are simulated at different multiband frequencies. The same design have a metamaterial behavior with its phase reversal graph, where the resonant frequency band shows both metamaterial and fractal antenna characteristics. This antenna is also useful for radar, mobile, and satellite communication services. The future scope for this metafractal antenna is that it is a very new design in the field of antenna research. So there is a much scope of work in this field, and the proposed antenna will be tested on a site analyzer for multiple applications. And the design can also be improved by various parameters like antenna size, antenna element, feeding method, and the substrate. These are the 7 important references. Thank you.
Any question from the jury?
Log periodicity is a relationship. What is meant by log periodic shape?
Yes, sir. The log periodic shape concept is used like fractal has a scaling factor which should be used in the structure. In the same way, the design I have used, the length, the gaps between the rings, the slots between the rings are in log periodic manner. That means the length of the inner ring to the outer ring, like L2 by L1, and the width between the two rings, outer two rings and the inner two rings are in log periodic ratio, that is 0.8 in nature. So for log periodic I use because log periodic antenna has the ratio from 0.7 to 0.95 scaling factor. So that's why I have used, this is a log periodic shaped antenna.
Where is your feed point?
Yes, sir?
Can you show the feed point? Which is your feed point?
So feed point is, so it's been shown.
That is the feed point.
Yes, sir.
How you are calculating S12?
So S12.
How you have found out S12? You are showing one feed point. How you are finding out S12 or S21?
I have not shown the simulated. So I have not shown the simulated HFSs. Yes, sir. Yes, sir.
How you are finding out that?
So actually I have used 2 feed points. I have calculated, I have not shown in the PPT, but I have calculated using a second feed point for this structure.
Phase reversal.
So this is S12.
Which one is your phase reversal?
So
how many phase reversals you are getting?
Yes, sir.
How many points you are getting phase reversals? And
so at 4.7 and 3.4076. So this is the phase reversal. And this is
Achha.
yes. So actually it's a multi-band antenna, so it is not a bit clear. So I marked the points M1 and M2.
Okay. Any other questions from jury? Okay. Thank you.
Thank you.
The next paper is Smiley Set Microstrip Patch Antenna for Multiband Applications. And author is Anu Sar.
A very good evening to jury, chairperson, and all the delegates. Today, I, Anukasha, here to present a smiley-shaped microstrip patch antenna for multiband applications. Objectives of smiley-shaped patch antenna. First is to design and develop high-gain and reduced size antenna for multiband applications. Second is flexibility to vary the dimension of slots to obtain different resonant frequencies. Design and design parameter. We have designed a new smiley-shaped antenna
Dimensions of patch. Radius of patch is 9.38 mm. Major radius of eyes is 0.65 mm. The ratio of eyes is 2.5 mm. The width of smile is 3.42 mm. The substrate used RT to write 5880. Relative permeability is 2.2 and the thickness of the substrate 0.787 mm. Novelty in design, compact size, multi-band and high gain. Simulated S11 parameter. These are three frequencies are here. At 4.9545 gigahertz is minus 15.8591 dB with bandwidth of 45.4 megahertz. At 5.8182 gigahertz is minus 27.2686 dB with bandwidth 87.4 megahertz. At 8.5 gigahertz is minus 22.6412 dB with bandwidth of 126.4 megahertz. Next is elevation and azimuth pattern. Figure A shows elevation pattern and figure B shows azimuth pattern of this antenna. Gain at 4.9545 gigahertz is 6.321 dBi. Gain at 5.8182 gigahertz is 7.2284 dBi. Gain at 8.5 gigahertz is 5.9633 dBi. The maximum gain has been achieved at 5.8182 gigahertz. Experimental results. Bird site analyzer ES6000 is used for measurement. The experimental results are almost similar to simulated result. Next is a comparison. The measure frequencies of the fabricated antenna are compared with the simulated result which are in good agreement. Conclusion and highlights of achievements. A reduced size antenna, it also gives high gain and bandwidth. By changing the dimension of slots, resonating frequencies change. Future scope. Various geometries can be used instead of circular. Parasitic elements can be loaded into the smiley shaped patch antenna in order to increase the performance. These are the important references. Thank you.
Questions from you?
Can you show the results graph, please? Comparison. Where is the comparison of the theory with experiment? Simulation with experiment.
This is a simulated S11 parameter and this is the experimental result of S11 parameter. Okay.
It's very difficult.
My first resonating frequency is a 4.9545 gigahertz and the experimental frequency is a 4.607 gigahertz. So small variations are there. And the second 5.8182 gigahertz frequency and the experimental 5.789 gigahertz.
Are these frequencies arbitrary? You have taken whatever frequency that the shape has given, or you have designed for this frequency?
Yes, sir, I have designed this frequency because my antenna applicable for public safety band and Wi-Fi and the biomedical application. Public safety is a 4.9545. This frequency is applicable.
How do you justify that it is a high gain antenna? You said that it's a high gain antenna. How do you justify it?
Because very small antenna radiate a high gain.
Any other questions?
See, this is radiation pattern 2. Yes. In one case, your antenna is radiating in broadside, and one case it is entering in the end fire, right? Can you give? No. You go in radiation pattern 2, only 2. You see In one radiation pattern where you have set your marker, your main beam is pointing broadside, right?
Yes.
And in the other case, it is in the infrared direction. Can you please explain? She is getting discrete band.
Okay, thank you very much. Okay, the next paper is dual narrowband design of rectangular ring slot antenna for 2.45 gigahertz wireless communication. Author is Binaban.
Good evening to all of you. Myself, Bilal Bakri. I am pursuing MTech from B19 Nagpur. I am going to present dual narrowband design of rectangular ring antenna, ring slot antenna for 2.4 and 5 GHz wireless communication. The main objective of this paper is to achieve dual narrowband at 2.4 and 5 GHz both. Both bands are ISM bands which are license free. In this design, I achieved stable gain for both of bands which will be applicable for wireless applications. The design of proposed antenna, my rectangular microstrip antenna is designed on RT Duroid 5880 substrate which is having this specification 1.6 mm thickness, dielectric constant 2.2 and simulation is done by Nsoft HFSS software. The radiating element patch which having the dimension of 47 cross 39 is calculated from standard formulas which is given in the literature and it is mounted on the substrate of 80 cross 70 mm. Due to my requirement of narrow band antennas, perfect electric conductor is used as a ground plane of the same dimension as substrate. In the rectangular slot is employed between the radiating patch which is having the dimension of 1 mm width and the other dimension also here, this one. This is the design. Here, this is my patch and a new ring slot. Actually, ring is circular. Ring should be circular, but here it is as a shape of rectangular. That's why the name of my paper is rectangular ring slot antenna. Other design is sorry. The parameters are given here. WS, LS are the substrate width and length. WP, LP is the length and width of patch, and these are the parameters for ring slot. Feeding point location, which is calculated by standard formulas, and the location is 7.83 mm away from the top edge of the patch here, and 17.72 mm away from the side edge. The novelty in the design is ring slot, which I have employed between patch. The simulation result here, the dual band I am getting, this is for 2.4 gigahertz and this is for 5 gigahertz. The bandwidth I am getting is 58, here 58 megahertz and here 101.4 megahertz. The gain and radiation pattern are shown here. Maximum gain 6.54 for 2.4 gigahertz, and here this is for 5 gigahertz. I am getting approximate 4 point something, 4 point something. Conclusion: I found that in the radiating wedge, if we are employing any type of slot, it will give another resonance frequencies, and dual narrowband efficient impedance bandwidth is achieved using proposed antenna in this paper. Antenna is low cost, has a stable gain in both upper and lower band. Future scope: due to very small size and low cost, it is very applicable for LAN, Wi-Fi, for short range wireless communications. Proposed antenna can be modified for better gain by changing the substrate. These are the references. Thank you.
Questions from the jury? Any other questions?
Sorry? Hello? You are inside a rectangle, no? Small rectangle, ring. Is there any correlation between the resonant frequency? You have any idea?
Sir, before this rectangular ring employed, it was resonating at 2.4.
If I am increasing the size, what will happen?
Okay.
If you are increasing or decreasing, what will affect?
It will deviate from 5 gigahertz.
No, is there any effect? Yes or no? That's all.
Yes, of course.
If you are increasing the ring dimension, what will happen the resonant frequency? Increasing or decreasing?
Sorry.
No, we are inserting the ring, the small ring, and ring size is increases. What will happen the resonant frequency?
It will decrease. It will come towards 2.4, then 5.
No, sure.
What is the diameter of your ring? What? What is the peripheral dimension of the ring relative to lambda? That makes your answer. Your peripheral dimension relative to lambda makes the answer. Are you getting?
Yeah.
What is the wavelength, and what you calculate the wavelength and the peripheral dimension, take the ratio you see and compare.
Any other questions? Thank you. Thank you very much. The next speaker is A. Sakti, and the paper is Design and Development of Compact Metamaterial Based Tri-Band Antenna for WLAN Applications.
Very pleasant evening to one and all gathered here. So this is Shakti from Tyagaraja College of Engineering, Madurai, and I'm going to present my paper titled Design and Development of Metamaterial-Based Tri-band Antenna for WLAN Applications. So first of all, going into a project, we need to know what are all the challenges in our applications. So the first challenge is that spectrum crowding. As we know that ITU has made a statement that many applications are being devised at 2 to 4 gigahertz, and now the applications are being shifted to 5 to 7 gigahertz due to spectrum crowding. And next thing is interoperability. See, our device must be capable, since WLAN applications have a lot of standards, so our device must be capable of operating between those standards. So it must be capable of shifting between the standards at a particular time. Next is coverage and then cost, which is a very important challenge. Next thing is miniaturization. So when we take the real estate issues, there the antenna and battery size plays a major role. So in my project, antenna miniaturizing the antenna is a major thing which I have taken for my project. Next is the challenges in WLAN antenna design. Size is the greatest challenge, cost, performance, and then multi-band operation. So one single antenna must be capable of operating in 3 or 4 bands or multi-bands, which will be an advantage for this. So after learning the challenges, I have derived the objective of my project, which is to design and develop a compact tri-band antenna using complementary split ring resonator for WLAN applications. So this is the design flow of my project. So first we have to design the specifications for the project, for the paper, and then technology choice, what kind of technology I am going to choose for this paper, and then proposed structure followed by the design of the antenna, and then fabrication and testing. So these are all the specifications we have derived for the paper. The frequency band is from 5 to 7 gigahertz. Bandwidth is around 40 megahertz. Since we are using CSRR, ultimately it will be having inductive and capacitive effect. So the Q factor increases, thereby it creates some problem. And next is the gain, then antenna size. Substrate which I have chosen is glass epoxy, easily available. Substrate thickness as 1.6 mm. So this is the proposed structure. So the inspiration of my paper is from Tatsuhito's sir's work, and in that work he has introduced the CSRR design has been introduced on the patch, but below the patch he has given introduced AMC structure. So in case of introducing AMC structure, you'll be having in-phase radiation. So because of in-phase radiation, you'll be having a good radiation pattern obtained. But in my design, I've just tried out by by removing that AMC, I've just tried out by using a common ground, normal ground without AMC. So this is what I have given. Conventionally CSRR is, and another novelty is that CSRR conventionally in all papers, it has been etched on the ground plane to improve the resonance. But in my work, I've just tried out whether CSRR, if it is etched on the patch, what happens to the structure is my entire paper. So these are the simulation results I have obtained. The bandwidth is narrow because of CSRR, and I have used CST Microwave Studio for my paper. The antenna dimensions as I have given in the specification, it's around 11.87 plus 11.87. Feed length is around 12 mm, and the optimization is done by varying the width and length of the middle CSRR. So here comes the question, why we are going to optimize the middle CSRR. The reason is that the middle CSRR, the middle CSRR is present just below the feed leg. So what happens is that maximum amount of energy is being spent in this region, and you can very well see here that this particular frequency has a very good return loss. So this is one of the observations which I have made from my work. And then these are the radiation patterns. So this is a spherical coordinate radiation pattern where we have theta and phi. And in that particular region, I have measured the radiation pattern for 3 frequencies, that is tri-band frequencies I have just measured. And you can very well see that it is more than 3 dB.
कैमरे तो रहने दो.
So regarding the analytical results, I've just checked whether increasing the field width in in first structure, you can very well see that by increasing the field width, what are all the observations I've just noted out the observations. And in second structure, if we increment the middle CSRR's length, then what are all the variations is being seen. And in third structure, I've just reduced the width of the entire width of the middle CSRR. So entire width of the middle CSRR, here you can very well see that because there is no proper matching, the third frequency has not occurred. So this is one of the observations I made. So these are the experimental results. Obviously, I made the structure with we didn't go for machine fabrication. We just made with the help of our mentors. We just made ourselves. So there is a slight shift in our frequency. This is our simulated result. There is a slight shift in frequency. Maybe due to improper fabrication, there might be a slight shift. And you would have seen this is our chamber measurement which I have done, and I have also calculated the gain. I have had a high gain antenna and a DUT. I have measured the distance and I have calculated the gain measurements also. So difference between DUT and then difference between the first measurement and second measurement, I have calculated the gain of the antenna. And so comparison between simulation and experimental result is that there is a slight discrepancy between simulation and experimental results due to less number of cells which I have taken. Since I have used CST, I have taken the upper limit and lower limit as 20 and 25. Maybe that might be a problem. Each and every point would have not been simulated properly. Then due to manual fabrication may be a problem. So conclusion is that a tri-band metamaterial based wireless LAN antenna in 5 to 7 GHz band is designed, fabricated and tested. So the highlights of highlights and achievements is that the novelty is the use of CSRR on the patch without using AMC as a background, and size reduction is also being realized considerably. So the future scope may be designing EM simulation with the help of numerical methods. We can do that. And with multiple CSRR, we can go for periodicity. So what I thought that instead of having one CSRR in the middle, we can have periodic structure so that maybe maybe you can have very good results for this. So these are the reference papers. So I've gone through Veslago's paper, 1968 paper, and then Ito's paper. So thank you.
Wonderful. Questions from you?
Somewhere you said about the compactness of the antenna. How do you justify this? How do you define that the antenna is compact?
Sir, if you go for tri-band applications, for one particular band, we must use one antenna, and for 3 bands, people are using 3 different antennas. But in my case, in one single antenna, by making use of CSRR, we are achieving 3 bands.
No, that's possible to achieve even 5 bands also.
What
I'm asking is, which antenna you call it as compact? How do you define a compact antenna?
Sir, we can take the formula lambda is equal to C by F root of epsilon effective, sir. So compactness comes whenever epsilon effective increases, again lambda decreases. So that can be a possible way for compactness of an antenna.
Your design specification was 5 to 7.
Yes, sir.
And your third resonance is occurring at 7.3 or 7.35.
Yes, sir.
So that is not in your specification. How do you justify that?
Yes, sir. That's what. Thing is that we have done some manual fabrication, sir. We didn't go for machine cut fabrication. So while doing manual fabrication, maybe there might be some intricacies done. But we are just going to. After going back home, we are just going to rework this paper, sir.
About simulation also. Simulation also, the result was beyond 7 GHz.
Previous.
Application-wise, okay.
Maybe, sir, maybe the patch size can be reduced to get a perfect band, sir, from 5 to 7 gigahertz. Yes, sir, 5.5 gigahertz is given. Yes, sir. For 7.5 gigahertz, what can be done is the center portion. I mean, periodicity can also be introduced, as well as you can have you can reduce the middle CSR strength.
We can discuss that later. Let me wait.
Thank you. Thank you very much.
Thank you.
That was the last paper of this session. Thank you, everybody.
For the benefit of the students, because this was a award session and there was some serious time constraints, we essentially cut short many questions and comments. For example, even I had questions almost on everybody, which I have sort of noted down, and I'm sure it is the case with many others. So the students who have presented, if they wish to, they could probably discuss with others and see if they would like to get the feedback. I do have some, if you wish to. I just want to make one general observation, not about the particular set of papers. Please think what would have happened if we don't have IE3D or CST. How you would have done your, gone about your designs and other things. So it really would make some impact if for 2 days, if you think that you don't have those licenses available with you and you have to work. And, it is because otherwise we are only being slaves of the software tools to come up with whatever you are coming up with. So please think beyond the tools if you really wish to understand what, let's say, antenna engineering is all about. Thank you all.
So with this, we have come to end of technical session of the third. So I thank the session chairs, jury members, and reviewers. I also thank all the delegates for cooperating and sitting up to this time. So now hands-on session will be continued in exhibition hall. So all the delegates are requested to take full advantage of that, especially students and research scholars are requested to take full advantage of that. Dr. Patnaik is already there to facilitate that session. So I request you all to take full advantage of that also. So thank you one and all. So we'll meet tomorrow at sharp 9 a.m. Thank you. Okay, about